Hello friend, my name is Imran Ahmed. In today's lecture we discuss about the Thevenin's and Norton theorem. So first we discuss about the Thevenin theorem. The basic definition of Thevenin theorem is that a linear two-terminal circuit can be replaced with an equivalent circuit of an ideal voltage source VTH in series with a resistor RTH. So what is VTH and what is RTH? Uh, we will discuss in next slide. So what is VTH? VTH is equal to the open circuit voltage. Clearly notice that VTH is equal to the open circuit voltage. And what is RTH? RTH is a input resistance that will be calculated by the replacement of independent source. So how to replace independent source? First we clear that what is independent source. Independent source may be either voltage source or current source. So if voltage source, so we can during calculation of RTH we should short circuit, and if an ideal current source, then during calculation of RTH it should be open circuit. So this is the Thevenin theorem block diagram. Here we can clearly see that this is the network and this is the load part where we want to calculate the Thevenin equivalent circuit, or we can say that we calculate the across A and B. This is the terminal, or we can say that this is the load. So what is the this network? Network can be consist more than two independent source or more than two dependent source. But for diploma student, generally we are talking about the only independent voltage and current source. So all the current and voltage source can be replaced by the one single voltage source and one single current in series with voltage source. So this is the load. This is the whole this is the our Thevenin equivalent circuit across the load. So how to calculate VTH? So here we clearly visible that when we draw a Thevenin equivalent circuit and when we open the load, so this is the open circuit, this is the open, and that's why this is known as a open voltage. And due to the open, there is no current in this. I is equal to 0. There is no current, so there is no potential drop across the RTH. So whole VTH will be equal to the VOC. That's why here we write the VOC is equal to VTH. So this is the helpful for the calculation of VTH. We know that in this slide we know that the VTH is equal to the open circuit voltage. In this slide we discuss about the how to calculate VTH and how to calculate RTH. So in Thevenin theorem or in Norton theorem we discuss later. First we define where we want to, or we can say that in which load we want to draw Thevenin equivalent circuit. So first point is that we should identify the load. We should identify the load, or we identify the terminal, which may be a resistor or a part of a circuit. This is maybe a resistor. Load is generally a resistor. So this is the first point where we how to find the VTH. Replace the load with an open circuit. And third point, calculate VOC. So how to calculate? When we open the load resistance, there is no current, and generally we apply KCL and KVL. We find the VOC, that is equal to VTH. This is all about the calculation of VTH. From fourth point, this is for RTH. So how to find RTH? So the first thing is that we turn off all independent voltage and current source. For example, if you have a voltage source, if you have a voltage independent voltage source, so it will be short circuit, and if you have an independent current source, it will be a open circuit. So in short circuit, this is the zero ohm resistance, and in open circuit, this is the infinite resistance, very high resistance. In other word, you can say that turn off all independent source. It means that if we have independent voltage source, it means that we can replace the independent voltage source its internal resistance, because in a voltage source have internal resistance is equal to 0 ohm. It means that it will be short circuit. Similarly, the current source have internal resistance is infinite. That's why it during finding RTH it will be open circuit. The question in for diploma students generally ask for the independent voltage source. We rarely see that the current source. So the second step to find the RTH is calculate the equivalent resistance. That is, this is our RTH. This is very easy to calculate the VTH and RTH. In next slide, we take example for better understanding. This is our general network consisting four resistance and one single independent voltage source. This is the 3-volt battery. This is the 12 ohm resistance, this is the 6 ohm resistance, and this is the 4 ohm, this is 2 ohm. But in question, the mention that we find the Thevenin equivalent circuit across the A and B. It means that find the Thevenin equivalent circuit across the load 2 ohm. So how to find the load Thevenin equivalent circuit across the 2 ohm resistance? So this is the first step. This is the first step to find. This is the first step to find the Thevenin equivalent circuit. So find the VTH. VTH means V open circuit. So replace the R load resistance with open. This will be open. So calculate. When we open the terminal A and B, there is current is equal to 0, no current, because this is the open, this is the infinite resistance. So whole current will be go in this loop. So the voltage VOC, or we can say that the open voltage, or we can say that the VAB is equal to the voltage drop across the 6 ohm resistance. So what is the voltage across 6 ohm resistance? We can use the voltage divider theorem. We can easily find the 30 into 6 upon 6 plus 12, that is equal to 10 volt. This is our VTH. So you can easily find VTH. This is our VTH. In next slide, we can find the RTH. So for RTH, here is the voltage source. So we can replace this voltage source 30 volt with the short circuit. This will be short circuit. So easily you can see that here is the short circuit. Here is the short circuit, and due to the short circuit, this 12 volt and this 6 ohm, it will be parallel. This is the parallel combination to find the equivalent resistance of 12 and 6 ohm. This will be, I think, 12 into 6 upon 12 plus 6, that will be 4 ohm. 4 ohm. After calculating 12 and 6 ohm, this comes the 4 ohm, and then the 4 ohm and 4 ohm, this 4 ohm will be in the series. So total RTS will be 4 plus 4, that will be 8 ohm. This 8 ohm is equal to the RTH. So this is very easy to find the RT. In next slide, we discuss about the Norton theorem. So Norton theorem is nothing but it's similar to the Thevenin's theorem. In Thevenin's theorem, we replace the network with a single voltage source with series single resistance. In Norton theorem, network we replace the network with a single current source with the parallel resistance Rn, and Rn is nothing but it's equal to RTH. It's the same. Thevenin resistance and Norton resistance both are same, so don't confuse it. Here is the one example for solving Norton's theorem. So here we can see that this is the voltage source, 28 volt, and here is a 7 volt, two independent voltage source. And in question, the load resistance is in question. It mentioned that to find the Norton equivalent circuit across the node A and B across 2 ohm. So this is our Norton's equivalent circuit. So how I Norton is equal to 14 ampere and R Norton is equal to 0.8 ampere. How to find it, we can see in the next slide. So this is our circuit, 28 volt, this is the 7 volt, and when we find the RTH, finding of RTH is very easy. When we find RTH, what will we do? Then A and B should be open. When we open, and this will be short, 4 ohm and 1 ohm will be parallel to each other across AB. So RTH will be 4 into 1 upon 4 plus 1, it means 5. It means 0.8 ohm. So finding of RTH is very easy. So the second point is that how to find IN, Norton equivalent current. So in this we can see that finding of IN, we should one thing notice that when we find in a Thevenin theorem VTH, Thevenin voltage, we will do open, but when we find the Norton current, we will do short. So this is the basic basic difference behind the Norton and Thevenin's theorem. So when we sort to find the IN, this is the IN current, this is the IN in this circuit. So finding of IN is nothing but apply KVL and KCL. This is very easy step to find KVL and KCL. This is the loop 1 and this is the loop 2, and easily we can apply KVL in loop 1. This is the I1. You find first I1 is the 7 ampere, and similarly in loop 2 we find the I2 is equal to also 7 ampere. So what is the IN? With main focus is that what is IN? IN is nothing but the I1 and I2 both, I1 plus I2. So this is the 14 ampere. This is all about the Thevenin and Norton theorem. We will discuss in next lecture with some other example. Thank you.